Welcome to the PropsClear podcast. I'm your host, Jillian Angeline. We'll be talking all about drones and about how to improve public perception surrounding the unmanned aircraft. Now, these discussions are for informational, entertainment, and educational purposes only, so they don't constitute legal advice of any kind. So fasten your seatbelts and let's get started. Today's guest is Dr. Adam Houston. He's a professor at the University of Nebraska-Lincoln, and he's also a lead of the Severe Storms Research Group. Thanks so much for joining me, Dr. Houston. First of all, tell me what the goal is of your work overall.
To better understand severe storms, and that's the hazards that they produce primarily, but you have to understand the storm itself, how it evolves, how it interacts with the environment before you can drill down into the specific hazards.
Now, the goal of this podcast is to talk about how to improve public perception surrounding drones. I saw some pictures of these awesome fixed wing, drones that you use to go in search of and to study storms. Can you first of all talk with me about what these look like, since a lot of people that may be listening can't actually see what these look like?
Yeah, when you hit the main distinction between it and most of other drones, and it's fixed wing. And it's a deliberate choice because what we're trying to do with a lot of the applications is fly into hazardous areas where rotary wing drones may not perform the best. We need a lot of flight time. So rotary wing drones, you have 20, 30 minutes at best for most of them. We need to fly for hours. And so you really need a fixed wing for that. We're going to be encountering winds that are very strong and sometimes even too strong for the fixed wings that we fly, but much stronger than the tolerances of most rotary wing. So the drone that we're using is primarily a foam body. It's 91-inch wingspan, so it's not small. It's small relative to commercial aircraft, of course, but it's very lightweight. It has a pusher configuration, so the prop is in the back. All the instrumentation is along the nose or inside the nose, and so we have all the communication equipment is there. It flies on autopilot, but as you know, we have to remain we have to have visual on it at all times. And so, while it's flying on autopilot, it's tethered to electronically tethered to a ground-based vehicle. So it's tasked to follow the GPS location of a ground-based vehicle, and then of course the pilots can control aspects of the flight, and they can take over manual control, which we do on both takeoff and landing. Or if they need to offset it from the road or avoid some kind of tower or something that's in the way, they can certainly do that, or take it up and down. And that has to happen quite often, particularly as we fly into storms and the visibility gets poor. They need to bring it down so that we can actually see it. So the aircraft does fly for a while. Like we have 2-hour nominal flight time, and it has it's electric powered. So it's not a combustion engine. It captures the typical meteorological observations, so temperature, moisture, winds, pressure. Winds are challenging on a fixed wing aircraft or pretty much any drone, particularly when it's getting buffeted by storms. There's lots of challenges in this environment. Winds happen to be one of the bigger of the challenges.
So now talk with me about the difference between using your own eyes, using the other instruments that you have at your disposal, like weather balloons, versus drones. Drones are kind of a new concept in the storm chasing field, at least relatively speaking. If you look at the last 150 years, what does it bring to the table compared to all the other instrumentation out there?
Yeah, and in and of itself, it's not going to give us everything we need. So we use mobile radars; those are invaluable. We use surface observation, so we have our mesonettes that we drive around, and those are invaluable. We use weather balloons because if you want to get a vertical profile of the troposphere, you have to have. Weather balloons are the best option right now. What we can't do with any of those others is get the thermodynamics in the storm. Actually in the storm, with a weather balloon, even with some of the balloons that we have where they kind of go with the wind, sort of, we don't have any control over them. And so we don't really know where they're going. In particular, one of the things we're trying to look for are these boundaries between air masses in the storm. And a lot of those kind of behaves material circuit. So in other words, a balloon that's launched in the storm doesn't really cross it. It kind of flows along. And if we want to try to cross it and get the structure of the boundary itself, it's hard to do with the balloon. The biggest issue, though, is the lack of controllability. With radars, again, radars are fantastic, and I can't imagine some of the projects that we do without them, but they're getting kinematics, they're getting the winds, they're not getting the thermodynamics, they're not getting temperature and moisture and pressure. And really, to close our understanding of the structures that we're focused on, we need all of it. We need the thermodynamics.
To confirm for everyone, you're not flying the drone into any supercell, tornado, or anything, or are you?
Not into the tornado. That's not. I mean, we certainly have been on tornadic storms, but yeah, the goal here isn't to fly into the tornado. We don't see really any value in that. The video would be pretty cool, but that's not what we're after. No, we are flying into the storm. We're flying into supercells, so we encounter rain and hail and high winds. And some of these make it difficult to operate the aircraft for sure. But not into the tornado itself. So really what we're trying to do is get the airflow that might end up in the tornado, but more importantly, the airflow, the conditions that go into the storm prior to tornado formation. So the precursor environment. So the idea here is to relate those environmental conditions, but also the internal structures of the storm that might differentiate between the storm that produces a tornado and ones that do not.
When was your first experience realizing that you could use this kind of aviation technology for your purposes in your severe storms research group?
Yeah, this was something that people have thought about for a while. I know that Eric Rasmussen and Jerry Straka back in the 90s were thinking about trying to do something like this. And the combination of engineering challenges and to some extent regulatory challenges, I think the regulations were more open back then. But yeah, they couldn't get it to work. And I think mainly it was the engineering aspect of it. And I came in, I was kind of at the time, kind of a young whippersnapper and thought, well, I could make this work. And not me. I can't do it by myself. I collaborate with the University of Colorado and have been for many years. Brian Argro and Eric Frew at the University of Colorado have been my collaborators for many years. And, between them, who are aerospace engineers, and me, an atmospheric scientist, we're able to figure out how to do this. And we started small. We didn't start by flying into supercells. We started by just ticking off the things that you had to do to get to that point. And there are a lot of them. But we worked incrementally. We figured out how to fly the aircraft with this electronic tether, which is a pretty cool thing. This follow me approach to operations is something they developed for this purpose. But even then, even with the software, you have all the other challenges of flying aircraft, and not to mention flying aircraft in the vicinity of storms.
Can you step back and ask and explain what an electronic tether is?
Yeah,
I know you
yeah,
gave kind of a short definition earlier. Could you, uh, as I said, I'm hoping that this is an educational experience for some people who may not understand what some of those concepts are.
sure. Yeah, yeah. So an electronic tether is communication to the aircraft that says follow the GPS location of a ground-based vehicle. So it's electronically tethered to that ground-based vehicle. And so the communication goes from the vehicle up to the aircraft, and then of course the aircraft has the GPS locations of itself plus the ground-based vehicle. And there's still variability, so it's not like it has to stay at exact point above the aircraft. We can offset it, we can put it forward or backwards, and as we drive, sometimes we drive too fast. Rarely do we drive too fast. Usually the aircraft is flying faster than us. But sometimes we'll drive too slow, and so the aircraft will orbit while we're driving. So they're kind of doing these kind of circular things. We're doing S's. We do try to keep the aircraft close. So if we're going, 50 miles an hour, but the aircraft is going into a headwind that's 50 miles an hour, then it's going to go slower. And so we have to slow down, let the aircraft stay with us. So it's not completely automatic, in part because we're limited by the engineering limitations of the aircraft. We're limited by regulations. But the basic idea is that the autopilot on the aircraft is set to follow this GPS location.
So is there someone actually piloting this aircraft on a joystick or anything like that on the ground?
Not when we're in our main operation. So when we take off yes. When we land, yes, but during the main part of the operation, no. I mean, it'll basically, even on takeoff, it's launched off of a pneumatic catapult on top of a vehicle, and so it's kind of shot off and it goes, and pretty shortly thereafter, after they just make sure everything's working right, they'll put it on autopilot. It'll spiral up to its cruising altitude, and then we go, and it just follows. Yeah, I mean, it's never that simple. Of course, there have been times where something goes something goes sideways, and we have to take it off the electronic tether. They jump out with the controller, and then they bring it down. But the nominal operating is that it's on manual at the beginning, on manual at the end, and the rest of the time, the vast majority of the time, is flying on autopilot.
Would you say that you helped bring this technology to the storm chasing world? I mean,
Yeah,
you were considering yourself the young whippersnapper at the time. What were you doing then that made you decide, hey, I want to try this out?
yeah. So a lot of the work that I did for my dissertation was on storms, but it was on air mass boundaries, and so these features that separate two air masses, and I was looking at how they might affect storms. And so my original plan was to really study those, not so much the internal dynamics of storms, but then how those boundaries affected storms. But to get the observations of these boundaries, you had to operate above the surface. Driving across these things at the surface was great, but you needed something above the surface. You needed more than just radar because you needed the thermodynamics. That was the main motivation, and I mean it was actually, that would have been frankly simpler than flying into storms, but it became apparent that there were a lot of questions that could also be answered by flying into storms. And so we leveraged that initial motivation and that the progress that we made early on doing the kind of small scale operations with drones, and got the funding to fly into storms and collect those data and really start to examine some of these internal workings of storms that you couldn't really understand with the existing technology.
So how many years would you say now have you been leveraging this technology?
Um, the grant that we got early on was in '08, 2008, and I the very first project that I worked on with Brian Argra at the University of Colorado was back in 2007. So we went out there um, and just basically started trying to figure out how to do this. I mean, he was not unfamiliar with the idea because Eric Rasmussen and Jerry Straka had been talking to him, and I thought, well, we could give this a shot, and we didn't just did it incrementally. We started small, came up with a project that could get funded, so we got some funding from the National Science Foundation, a very small project, and just basically needed to prove what we could do with it, and we proved it. We showed that we could do this, and then we got additional funding that leveraged that and got a bit more ambitious with it and participated in Vortex 2, which was a big project back in 2009, 2010, and flew into storms. Actually, for the first time, really flew into storms. Demonstrated that we could get some data, got some papers out of it, showed that we could actually do science with it. And then, a decade later, actually did it for real. I mean, it had, a big, an ambitious project where we're collecting lots of data on mini storms. And, in the interim, did small things with it. It wasn't just that we were sitting waiting for more funding. We were doing other applications of drones, both fixed wing and rotary wing, but always trying to advance the technology so that we could use that to do the real ambitious stuff.
Tell me how it felt emotionally speaking when you first realized that this actually worked. Maybe when you first lifted off that first, fixed wing aircraft, maybe when you finally realized you could get the funding to do something like this. How were you feeling knowing that it could become a reality?
Um, well, I mean, I was very excited when we got the funding to participate in Vortex 2. That was a huge project, and as a young scientist at the time, I knew that was a stepping stone to doing well. I mean, to doing stuff, not as just a stepping stone, but to potentially do some really interesting research and collaborate with some great people. But I also saw it as a stepping stone. I saw that was just a first step to doing the true in storm work. I was very excited to get that initial funding. And that wasn't the first grant. The very first grant was the small grant for exploratory research that Brian and I got in back in '08. But yeah, it's all been so incremental. It's not like it was just, well, I mean, the project, the funding to support Taurus, that was the project that I'm leading in 2019, and then 2022, and then a follow-on project related to it in 2023. The first funding that we got, I was very, very excited because we worked a lot to get that. We tried many times. It was not something where we submitted it once and got a chunk of money and were able to do this. So it was kind of a slow burn, but at the same time, I really felt like we had positioned ourselves to do it right.
And what does TORS stand for?
Targeted observation by radars and UAS of supercells.
So you got UAS in that title. That
Yeah.
That specifically talks about using drones for research purposes, correct?
Yeah. And in Vortex 2, we were kind of an add-on. We were kudos to the program managers who took a risk, because at that point we had never flown like that before, and they said, give it a shot, see what you can do. We also didn't have a whole lot of funding beyond that to actually do any analysis. So it was really just a proof of concept. We turned out we did some science with it, which was another feather in our cap. But it wasn't until Taurus that we really had dedicated funding to study supercells with UAS and other stuff. We had drones, of course, but we also had mobile radars and mobile mesonets and lidars and the P3 manned aircraft. But right, so it was an integral part of that project because of what it could do that none of the other instruments could do.
Now, I've talked with law enforcement leaders and other aviation leaders for the PropsClear podcast, talking with them to help improve public perception surrounding drones. A lot of people still have a lot of distrust, and the only way to get this whole concept and industry moving forward is getting the entire public on board. So a lot of the discussion that I've been having is all about how a lot of the work that drones do is to save lives. UAS does a lot of the work that makes our lives on the ground easier. And it sounds like what you're doing is also helping to save lives, because this research is going to improve warning times and do a lot of the work to get the research so that in the future people know about the power of storms, correct?
Yeah, I mean, one of the pillars for improving forecasting is improved understanding. So the drones will hopefully be one piece of our improved understanding of these storms, and then hopefully that understanding will improve forecasts. We can hopefully someday, and this is a whole nother project that we're working on, actually integrate drones, UAS, into the meteorological surveillance network. So the regular surveilling of the atmosphere, the regular observing, just like the radiosondes that are launched every single day. But instead of balloons, they're drones. And not only that, but they're in a lot more places than where the balloons are launched. And with something that's repeatable. So you can fly the drone up and down many, many times, whereas the radiosonde, it's a one and done. And so it plus you're not using helium, there's a whole lot of reasons, both practical, but also, fundamentally, we're looking at trying to improve forecasting, and improving understanding is a big part of that. But improving the data that forecasters have available to them is another huge step, because I had projects where I interview National Weather Service employees, have surveys, what data do you need, and they want more data. They want data that will help them make better forecasts. Drones may be one of the answers. It may be the answer. Maybe there are other things out there, but we have to at least go through the process of exploring it theoretically and then developing the technology to see if it actually makes a difference. And there's a whole lot of places that it can make a difference. It's not just you can plug it into a numerical weather prediction model. That's one thing that we're looking at right now. What happens when you take UAS data and you put it in numerical weather prediction models? Does it improve the guidance? And the answer is a lot of times yes. The next question is, what if you take those data and actually give them to the Weather Service forecasters, or any forecasters for that matter? What can they do with those data in their manual forecast, and there's evidence to suggest that it improves their forecast.
So you would tell someone who may not be familiar with drones, maybe has never seen a drone in their lifetime, that there are benefits across multiple industries for these flying objects, correct?
Oh yeah, absolutely. Yeah, and I hope that people see the benefit above everything else. Because I mean, I've been in this long enough. I've heard the arguments against it, and you've heard them as well. And some of them are legit, and we have to be mindful of that. We have to be mindful of privacy. We have to be mindful of the noise. We have to be mindful of all these things. Um, and in the context of being mindful, we also need to present them for what they are, which is a truly unique way of observing the atmosphere. And in that way, a truly unique way of potentially improving forecasts.
Those are all excellent points. One other thing you mentioned earlier is talking about how you had to see the drone consistently. A lot of discussion about around beyond visual line of sight is happening right now. I know there were a few waivers that went out in the September timeframe. So tell me your thoughts on what you'd like to see for beyond visual line of sight. For anyone that doesn't know what BVLOS is, it basically allows people to fly their drones, companies to fly their drones without actually seeing them, beyond where they're actually operating them or flying them. How do you feel about that, and what would you like to see for forecasting and research purposes?
Yeah, BV loss has to happen. I mean, that the bottom line. There have been so many times that we've envisioned ways that we can use drones for our research, and we hit a wall because we can't fly beyond visual line of sight. It's remarkable that we were able to do some of the stuff that we did for Taurus and other projects, not flying beyond visual line of sight.
Mhm.
But boy, the things that we could have done if we had been able to, it would have opened up a lot more options. When it comes to flying them on a regular basis for the meteorological observing network,
Mhm.
um, yeah, there's really no other way. You Even in the simplest operations, it doesn't make sense to have a person watching this aircraft at all times. We need too many of them, very likely. They need to be flying a lot, regularly, but from remote locations. It just doesn't make sense to have them set up where they have to have a person dedicated to watching it, let alone operating it. And of course, it doesn't mean that they're not being seen by people. Of course, they will be monitored. They'll have all kinds of equipment for real time situational awareness. It's just that there may not be, and there cannot be, a human being with eyes on the aircraft at all times. It makes it's an artificial limit, one that we have the technology to overcome right now. It's just a matter of proving that it works, and proving that it works on a regular basis. But at the same time, also having the counterpoint, that not the counterpoint, but having the other point, which is, here's the value. I mean, here's what these can do for us. When you relax the regulations, here's what we can do. And I think that's the ultimate testament for the ultimate argument for making some of these changes to the regulatory environment, is actually demonstrating that there is very real practical, value to them. And I mean, I of course will always say they're going to improve my research. They're going to improve our understanding. And I can say that until I'm blue in the face, but we also need more practical applications. That if we take these data and we give them to a forecaster, it will improve their forecast. If we take these data and put them into a numerical weather prediction model, it improves the model guidance. I mean, we need that other part to the argument, besides just that technology can do it.
Well, the other thing is, when you're thinking about BV loss for package delivery, BV loss for drone as a first responder, taking off a rooftop. A lot of times you need good weather in order to do a lot of that work. You all are risking your lives having to get extremely close to storms to then launch these drones into or near supercells. So BV loss would probably make it easier and safer for you all to do your jobs, correct? So that you're not so close to the storms yourself.
Just to some extent, yeah. For for Taurus and other similar projects, we benefit from having observations on the ground at the same time. So kind of this flying tower going into the storm. I even if we didn't, even if we could fly beyond visual line of sight, I still would have been in the vehicle below. Flying into or driving into big hail, that's something that we can protect against. We're not going to. It will damage the vehicle, of course, but I'm not as worried about people when in those environments. There are lots of hazards. I mean, I'm not going to minimize the hazards for sure, but for some of the research, I think I still would have had a ground-based vehicle with people inside underneath it. However, there are things that we can't do even in that situation because we can't fly BVLOS. For example, we can't fly into cloud. We can't fly into conditions where the rain is so heavy that it's hard to see. And those are observations that are really important because some of the structures that we think are important for determining whether a storm produces a tornado are right on that boundary where you go from no rain or light rain to heavy rain and hail, where the visibility goes to zero. Because there are times we flew into, we're like, well, we can't see the aircraft. We have to get out, even though we know this is an important part of the storm. So yeah, even with a person there underneath the aircraft, flying BVLOS still would have improved our ability to collect the data we need in Taurus.
I've been asking everyone, all the experts that I talk with, where they see the industry going in the next 5 years. It sounds like you obviously want BVLOS to be part of that equation. Is there anything else that you see being a positive or on a hope list for the next 5 years?
Well, I mean, one of the things that has improved a little bit is battery technology. We're flying electric vehicles for a lot of reasons. I think improved battery technology would be huge. 2 hours is great. 2 hours is not enough to do a lot of the stuff that we envision. We need to be flying 6 to 12, and that's a different type of aircraft probably. But what we ideally want to have is an aircraft that's still relatively small, has a pretty small footprint, if you will, but can fly long distances and fly fast if necessary. And so having really sophisticated batteries that can produce a lot of power, but also a lot of power for a long time is really, really critical. And then we've considered other types of power systems, fuel cell and whatnot. But right now we're kind of in this, what's the opposite of a sweet spot? The opposite of a sweet spot. We're in that spot where we have an aircraft that's so small that we can't put enough power in it to fly long distances. But if we go much bigger, then it becomes unwieldy. It becomes difficult to operate, to land and launch easily.
It's a big issue with advanced air mobility too.
Yeah.
They're talking a lot about AAM right now across the country and across the world, being able to transport people. A lot of that discussion is around the battery life because the batteries only last, 40 minutes or something very short. So it can't get very far from one metropolitan area to another. So it's not just the smaller drones, but these are the giant, people carrying vehicles
Sure.
that are also being, battery storage is a huge drawback, I guess, at the moment.
Yeah. And I mean, I wish I could. I don't know a lot about the future of battery technology, so I can't say whether the trajectory is good. I think the fact that electric vehicles, both small and large, are becoming more popular. I think market forces will drive innovation, and I hope they will, and that we'll see more, better batteries, or something different. Something that's not a combustion engine, but that gives us the kind of longevity that we need. There are other technological challenges that come with flying and precip that we need to overcome that we can. But again, we're kind of in a weird spot where commercial aircraft can do it, but because they're big, and you can put the sensors on a commercial aircraft and they work just fine. You can heat them, you can get rid of all that. But with these small aircraft, boy, it's tough. So yeah, I'd like to see innovation when it comes to relatively small aircraft for the atmospheric science applications, I'd like to see, of course, better battery technology, and whatever that solution is that allows us to fly BVLOS. If it's onboard radars, if it is, maybe it's ADS-B. I kind of doubt that FAA is going to go that route. I don't know what it is, but whatever the technology is that allows us to fly BVLOS, and the FAA to be comfortable enough with it. And they're never going to be comfortable with it, but I mean comfortable enough, that they can allow us to do it and not have so many hurdles that have to be jumped.
I assume you can fly your drone in rain and in other elements. So when you were talking about elements, are you talking about ice coating the wings, or what exactly were you referring to?
Well, so I mean that is one thing. Icing is we didn't encounter any of that because we're flying in the warm season, but yeah, that's something that we would need to deal with. No, the issue that we see is that we can fly in rain, we can even fly in hail, but rain tends to clog the pitot tubes, and so there are ways to flush them. There's ways you can push air out through them. You can heat them up. But
Can you tell
all
me what
those,
the pitot tubes are?
yeah, so the pitot tube is essentially just a small tube that's open on one end that allows air to essentially stagnate in it, and the pressure within the tube is an indication of how fast you're going. But we have sophisticated pitot tubes, the multi-hole probes that have multiple holes around. So if you imagine like a finger, it's about that size actually, they have holes around it. The pressure distribution around it gives you a sense for the wind relative to it. So if you have wind coming from one direction, you can kind of see based on the pressure distribution what that direction is, and both up, down, left, right, everything. So it's really important with an aircraft that is not just fixed in the flow, but there's a lot of body relative flow that not just the attitude of the aircraft, but the distribution of wind relative to the aircraft. And so these pitot tubes are great because they give you that. The problem is that they're little bitty holes that are exposed to the environment, and so they get clogged with rain, and they're not functional at all. So that was an issue, and it has been an issue. And again, with these small aircraft with not a whole lot of power, we don't have a lot of flexibility in removing the water from the pitot tubes.
Ooh.
Yeah, I know, right. And I remember talking to somebody before about this, and I said, yeah, sometimes we have problems in rain. Like, well, but you fly in rain. Like, I know, but there's still a problem. It's still like technological limitation that is hard to overcome. And I mean, there are other ways to get wind, but they're not as good. And particularly if you want to get the vertical component to the wind, if you want to get the updrafts and downdrafts, it's really hard without it. Well, it's almost impossible without this multi-hole probe solution.
And it's a sensor, basically, these pitot
Yeah.
tubes.
Yeah. So I mean, within you have the kind of the nose that has all the holes, and they have all these little tubes that go through it, and they go back to the sensor board, and they can detect the pressure, and they get the pressure differential, and then you calibrate it, and you can say this is the angle of it, all the stuff you need, all the essentially the wind relative to the tube, the multi-hole tube, and then from that you can back out what the wind in all three dimensions is, and so the X component, Y component, Z component.
For many, storm chasing and seeing storms is kind of this elusive, incredible experience that a lot of people hear about from movies, but they don't actually get to see in person. You've gotten to see so many throughout your career. What kind of lasting words do you have as we close out this discussion for many who may not see storms up close, and you not only get to see them, but send technology into them too?
You certainly get an appreciation for the beauty but also the devastation of Mother Nature. I mean, at the risk of waxing philosophical too much, I mean, I think it certainly gives you an appreciation for the importance of predicting these things, because we don't have control over the storms. I mean, the best we can do is understand what they're going to do to the best of our ability, and give people as much advance notice, and not just advance notice, but accurate advance notice. And so, I think that if anything, me being out there has shown me, just underscored. I mean, something that I kind of knew already, but underscored the importance of this work, and not just this one research project, and not just the papers that come out, the science that we do with these data that we collected recently, but this whole effort of trying to improve our understanding and our forecasting of these beautiful but very dangerous products of the atmosphere. And I think we can make progress, and we can improve our understanding. I think we can improve our ability to forecast them by giving better data to forecasters. And drones may play a role, and maybe they don't. I mean, maybe it's something else. But I think we need to ride this horse for as long as we can, and see what we can get out of it. And there's a lot of questions that we have to answer about its utility, and then until we kind of exhausted that and discovered how feasible or infeasible it is, I think we are still at the point now where this holds promise.
You're in a unique position where you can test a lot of the work that may end up in the private sector. You're in that research band, correct?
Yeah, absolutely. Yeah, I mean, I have colleagues who have gone over to the private sector to do basically leveraging the work that they've done in academia as researchers. I mean, I think there is absolutely a role that the industry and academia, that relationship is so powerful. I mean, we've absolutely benefited from it, partly because we have students who go out into industry and can take what they know, what they learned from academia, and develop products, and continue to innovate. And plus, then that they take this back to us, and we have this great synergistic relationship. And I think that's going to happen more. I mean, I think in some ways, maybe one of the avenues to make real what we are thinking is theoretical is through that route, where we basically say, look, I mean, the only way we're going to prove this is to do it. And sometimes to do it requires money beyond support, not just money, but support beyond the traditional federal agencies. I mean, I don't know. I don't know what this. So far, we've been successful in getting federal support to do a lot of what we're doing, but there may come a time where ultimately, if we're going to prove this, we got to, do something different.
Well, I'm certainly excited to see how your work evolves. Thank you so much for your time. I really appreciate it, Dr. Houston.
My pleasure.
Thanks so much for watching. Be sure to follow PropsClear wherever you listen to your podcasts. You can also subscribe to my YouTube channel to watch the videos from these interviews. If you have any topics or suggestions for future shows, email me, angelswings.jillian@gmail.com. That's ANGELSWINGS.JILLIAN@gmail.com. I'll see you later.